Welcome back, friends. Today I am going to show you some basic problems on pumps and turbines. Before I proceed to that topic, let me speak a few points on pumps and turbines. So pumps and turbines are just hydraulic machines, and they are used to effect an exchange of energy between mechanical and fluid system. So when we say pumps, just they are a means of adding energy to water, and they convert mechanical energy, which is imparted by just rotation, into hydraulic energy used in lifting water from one source to higher elevation. So types of pumps, you have just positive displacement pumps and rotordynamic pumps. So positive displacement pumps just consists of ram, piston, and also valve arrangement. So you have an example reciprocating pump and rotary pumps. And when you say rotordynamic pumps, just rely on rotational movement just for their pumping action. It relies on rotational movement just by the help of impeller. Examples, we can take centrifugal pumps, axial flow pumps, and mixed flow pumps. So I think once we have these pumps, I think we have again turbines. And the turbines are a means of taking energy out of water. So when we build a dam, we are creating a head of water. So this will be converted into high kinetic energy, which is due to the flow of water. Then before it impinges into the scroll casing, which is the shaft or just the runner. So just they convert hydraulic energy into mechanical energy, and the shaft, which is connected to uh, the turbine, which is connected to the turbine, is just coupled with electric generator that will produce electrical power. So we have two types of turbines. The first one is impulse turbine, and the second one is reaction turbines. So I think we have impulse turbine, which is just the pressure energy of water is just converted into kinetic energy before it impinges into a rotational element. We can take example Pelton wheel, which is just the impact of jets of water to a series of vans of the Pelton. And reaction turbines, just water is directed to the runner by means of a scroll casing, which is just we have Francis turbine, Kaplan turbine, and also propeller. So these are main examples. So we will go to the detail after a minute. In fact, I will come back with hydraulic machine, which is a detail of pumps and turbines. So let's go to the best illustrative examples on pumps and turbines. So let us start with the first example. So the first example is water from a well is to be pumped to a height of 40 meters from the source, and the quantity of water to be delivered is 500 liters per second through a 480 millimeter diameter pipe. It is also desired to maintain 100 kilopascal pressure at a set. So the frictional head losses from the suction and discharge of the pump are equivalent to 2 meters if the pump speed is 850 revolution per minute. Determine the power needed by the pump in horsepower. So this is the arrangement you can see. So the elevation difference from the source up to the reservoir is 40 meters, and at a summit it will attain 100 kilopascal. So what will be the power needed by the pump? So let us see the detail now. So just solution, solving the water power just from source, which is suction lift you have. So we have water power. So total dynamic head we have static head plus HV, which is very important, which is velocity head plus pressure head plus head force. So we have static head, which is this one, 40 meter. Then solving for the velocity using continuity equation, which is Q is equal to A times V, 50 meter cube per second. You substitute, then pi over 4 d square times b2. So we get this result, which is the velocity. The velocity in the pipe, which is in the delivery pipe, is in this one. So once you get this velocity, now let's continue neglecting the velocity as suction. If you neglect the velocity as a suction, we have velocity hv, which is the velocity head v2 square minus v1 square. Then you substitute here 0.763 square minus 0 square over 2g. We get this result, which is 0.3891. Then the pressure head is again given by the difference in the P1, P2 minus P1 over gamma. So we just substitute, then we get this is 10.1937 meter and head loss is 2 meter. So you can calculate now total dynamic head, which is 40 plus 0.381891 plus 10.1937 plus 2, we get this result. So total hydraulic, which is total hydraulic or water power, is given by rho g QH. So gamma, we can take this is gamma, unit weight of water. So gamma of water is 9.81 kilonewton per meter cube. Then you can substitute just gamma Q times H. So we have 0.5 meter cube per second times H. Then we get this is the power. So in horsepower, you can convert into horsepower. So 1 horsepower is 746 watts. 1 horsepower. We know 1 horsepower, 1 HP. 1 HP is 746 watts. Clear? 7, then 4, 6 watt. Clear? 746 watt we have. Then you can convert just into kilowatt. So 257 multiplied by 1 horsepower over 0.746. So we get this the power which is needed in horsepower. Okay, second example is just it is required to deliver 0.048 meter cube per second of water to a height of 24 meter through a 150 millimeter diameter pipe and a 120 meter long by a centrifugal pump. So if the overall efficiency of the pump is 75% and the coefficient of friction 0.01 for their pipeline, find the power required to drive the pump. So this is also power calculation. So we have rate, discharge rate, Q is given 0.048 and height, which is static height, which is static head. We have HS, suction head plus delivery head will be 24. We are given total. Then diameter, which is diameter in section and suction and delivery pipe, the same. We have 150 millimeter pipe, then which is 0.15 meter, and length of suction and length of delivery. We have total length, we have 120 meter. Overall efficiency is given and coefficient of friction is given. So first, power required to drive the pump, just P will be, you have to compute just other parameter, which is the net head available. So first, the velocity of water, which is in suction and delivery equal flow rate over area of the pipe. Then we get this value 2.7 meter per second. Loss of head due to friction in pipe according to Darcy-Weisbach equation. We have 4 g square over this e to g. So we have 11.89 meters. So this is the loss. So we have to compute the net head. So net head available, which is just you have suction head here, suction head. Then we have delivery head. Then just this is the arrangement, which is the screen, which is the strainer, just to avoid debris and floating materials from entering into this conveyance system. So we have just here we have pump, then it will go to this reservoir delivery pipe, which is delivery head and suction. We have suction head. Then let us calculate now. So the manometric head is given by this equation. So static plus HD, which is Z1, Z2 minus Z1, second reservoir, upper reservoir minus lower reservoir source, which is HS plus HD, then HFS, which is loss of head due to suction, loss of head due to delivery, then velocity, which is delivery square over 2G. So just we have here total 11.89 we have, and 24 we have total static head, then v square over 2G, we get this result. So this is the manometric head available for just power generation. Then you have to compute overall efficiency. Already we have, this is the output power divided by input power. So this is the shaft power to drive the pump. So we get this, just rearrange the equation, just crisscross, then we get just 22.76 kilowatt. This is the power by the pump. And the third example is centrifugal pump. So we have a centrifugal pump lifts water under a static head of 36 meters of water, of which 4 meter is suction lift, and the suction and delivery pipes are both the same diameter, equal diameter. Then the head loss in the suction is given 1.8 meter, in delivery 7. Then the impeller is 380 millimeter diameter and 25 millimeter wide at the mouth, and revolves at this rotational speed 120 revolution per minute. Its exit blade angle is 35 degree. If the manometric efficiency of the pump is 82%, determines the discharge through the pump and the pressure at the suction and delivery branches of the pump. So this is the pump arrangement. We have total head from here up to here, from the source up to upper reservoir. So we will use Bernoulli's equation, which is very important to compute total head loss. Then we have an arrangement, delivery head and suction, which is very important. Just below the pump, we say suction because it is negative. It will take water to this pump. Then after that, it will go to the upper, which is delivery head. Now, let us see solution. Solution is very clear. So first, we have static head, which is 36 meter. Suction lift, we have HS 4 meter. The diameter of each suction and delivery pipe is the same, which is 150 millimeter, converted to meter, 0.15 meter. Then the head loss in the suction pipe given already, we have HFS 1.8, HFD 7 meter already given. So diameter of impeller at outlet, which is D2 380 millimeter, then 0.38 meter, and width of impeller at outlet B2, which is 25 millimeter, then converted to meter 0.025. Now, speed of the impeller also given, and outlet blade one angle, which is given. This is the angle. So I will show you the velocity diagram. So manometric efficiency is this one. Then the discharge through the pump already. First, we have to compute manometric head. So the manometric head is this one. HS plus HD, static head plus delivery head plus head loss due to suction, head loss due to delivery. So we have this 44.8 meter. So once we have static head, which is 36 meter, which is given, then we can compute the other parameters. So this is the velocity triangle. This is the velocity triangle diagram. So this is outlet, which is just very important. Just when flow is going to this direction. So we have ones in the impeller. We have ones. So we have R1 and R2 to the top. Then we have, this is the angle, which is blade angle, which is outlet blade angle, which is this one. So you have the velocity, which is tangential velocity U2, and this is relative velocity, which is VW2, which is beta. Again, we have such velocity diagram, and this is the inlet. Then at inlet and outlet, once we have, then let's continue solution. Tangential or periphery velocity of the impeller is given by this equation, pi d n rotational speed. You have to convert into meter per second by this equation, pi d to n over 60, then we get 23.87 meter per second, assuming the flow at the inlet to be radial, which is alpha 90 degree. Just at the inlet, it is radial, which is 90 degree. Just this is our assumption. Otherwise, it may be given an angle. So work done per unit weight of water will be just this equation, which is velocity times U2 over G, and manometric efficiency is given by manometric head over this one. Work done per unit weight of water. Then we have this equation. Then once you just rearrange this equation, then the velocity, which is this one, will be 22.45 meter per second. Then using this equation again, you can find outlet blade angle with respect to velocity triangle from the above, which is Bf2 over U2 minus Bw. Let me show you again. So this is the inlet, which is inlet diagram, velocity triangle diagram. You have U1 and just this is tangential, and then this is going. Then we have assumption 90 degree. Then it will go like this. Then in the outlet you have outlet blade angle. Then at this point we can find velocity, which is final velocity, which is df2. Then you have tangential U2 total from here up to here. Then this is bw2, which is with respect to V2, which is beta with angle. Then you can find Vf2. So once we have 35 degree, which is blade angle, outlet blade angle, this angle is given. Then just crisscross. Then Vf2 will be this one, 0.99 meter per second. So the discharge is given by this one, area times velocity final. Then we have this result, which is 0.0295 meter cube per second. So this is the discharge. So once you calculate the discharge, then the pressure at the suction and delivery branches of the pumps can be computed using this equation. So ds or dd or dq over area, we have this one. Already once you compute discharge, then you can compute velocity, which is 1.67. Then velocity head, you can compute v square over 2g and vd square over 2g. Since we have the same diameter of the pipe, then we get 0.142 meter. The total effective pressure on the delivery side, HD plus HFD plus Vd square over 2G. So this is the velocity head in the delivery pipe. So we have this one, 39.142 meter of water. Then you can compute by this one, just this is the pressure head. Then pressure head, which is H equals P over rho G, Q over rho G or gamma, you can say. So if you crisscross, so you have gamma of water 9.81 multiplied by this pressure head, you get 383.98 kilometer per meter square. So this is the total pressure. So P is gamma times H, then where HD is static head minus suction, you have 32 meter of water. So pressure on suction side, again you can find HS plus HFS plus dx square over 2g. Then you have 5.942 meter of water vacuum because it is below the pump, and you can subtract now 10 minus 5.942, then 4.058 meter of water absolute. This is absolute. Then you can convert into pressure 39.8 kilonewton per meter square absolute. So these are the pressure at the delivery side and suction suction side. So I think these are important. So I will continue with the next example after a minute. So I think thank you very much for watching this video. If you have any question or doubt regarding these tutorial problems, please forward through comment suggestion box and I will reply on it. So thanks again.